Hello everyone, welcome back to probabilistic models course. In the previous session, we studied parameter estimation, maximum likelihood estimation, estimator properties, sufficient statistics, Bayesian estimation, and MAP estimation. Today, we move to a very important topic in stochastic modeling, which is Markov processes and Markov chains. The main idea of this session is simple but powerful. We want to model systems that change over time. For example, weather changes from day to day, a queue changes as customers arrive and leave, a machine changes between working and failed states, and a user may move between different pages of a website. In many such systems, the future depends mainly on the present state. This is the Markov idea. In this lecture, we will define stochastic processes, the Markov property, discrete time Markov chains, transition matrices, multi-step probabilities, Chapman-Kolmogorov equations, communicating classes, recurrence, transience, periodicity, stationary distributions, absorbing chirps, chains, and a short introduction to continuous time Markov chains. The goal is to understand both short-run prediction and long-run behavior. Okay, this slide shows the roadmap of today's lecture. We start with the stochastic process. A stochastic process is a collection of random variables indexed by time. We write it as x sub t, or as the sequence x0, x1, x2, and so on in discrete time. Then we introduce the Markov property. The Markov property says that given the present state, the future does not depend on the full past history. In simple words, the present state summarizes all relevant information from the past. After that, we define the transition matrix. The transition matrix P contains all one-step transition probabilities. If the chain is currently in state I, the entry Pij gives the probability that the next state is J. Then we study state structure. We ask questions such as which states can reach which other states, which states communicate with each other, are there closed classes or absorbing states, are states recurrent or transient, are they periodic or aperiodic. Finally, we study long-run behavior. We solve the stationary equation pi equals pi p, and we discuss when the distribution of the chain converges to the stationary distribution. So the full path is stochastic process, Markov property, transition matrix, state classification, and long-run behavior. Okay, a stochastic process is a collection of random variables indexed by time. We write it as the set of x sub t, where t belongs to a time index set t. The time index can be discrete or continuous. In discrete time t, t is usually the set 0, 1, 2, and so on. For example, x0 may describe the system today, x1 tomorrow, x2 the day after tomorrow, and so on. In continuous time, t may be the interval from 0 to infinity. In that case, x of t describes the system at any real time. The value x sub t is called the state of the system at time t. The set of all possible values is called the state space, usually written S. For example, in a weather model, the state space might be sunny, cloudy, and rainy. In a queuing model, the state space might be 0, 1, 2, 3, and so on, where the number represents the number of customers in the system. The important idea is that a stochastic process describes random evolution over time. Instead of only studying one random variable, we study a sequence or family of random variables connected through time. The Markov property is the central idea of this lecture. In discrete time, it says that the probability of the next state depends only on the current state, not on the full previous path. Mathematically, we write p of xn plus 1 equals j, given xn equals I and xn minus 1 equals I, n minus 1 and so on up to x0 equals I0 is equal to p of xn plus 1 equals j given xn equals I. This equation means that once we know the present state xn equals I, the older states x0 through xn minus 1 do not give extra information about xn plus 1. The past can influence the future through the present, but after the present is known, the full past is no longer needed. This is not always true in real life. It is a modeling assumption. The art of Markov modeling is to define the state carefully so that this assumption is reasonable. For example, if today's weather alone is not enough to predict tomorrow's weather, we might define the state to include both today's and yesterday's weather. In conditional independence, notation, we can write xn plus 1 is conditionally independent of x0 through xn minus 1 given xn. This conditional independence is what makes Markov chains mathematically traceable. Okay, a discrete time Markov chain is a Markov process where time moves in integer steps and the state space is finite or countable. We usually write the state space as S equals 1 to up to M for a finite chain. The one-step transition probability from a state I to a state J is written Pij. Formally, Pij equals P of xn plus 1 equals J given xn equals I. This number tells us how likely the chain is to move from a state I to a state J in one time step. If Pij does not depend on n, then the chain is called time homogeneous. Time homogeneous means that the transition rules do not change over time. For example, the probability of moving from sunny to rainy is the same today, tomorrow, and next week. At every step, the chain is in some current state I, and then it chooses the next state J according to the probabilities in row I of the transition matrix. This simple rule can model many systems: weather, queues, reliability, genetics, finance, user behavior, and many others. The key modeling choice is the definition of states. If the states contain enough information, the Markov property becomes a useful approximation. For a finite Markov chain, all one-step transition probabilities can be collected in a matrix. This matrix is called the transition matrix and is usually written P. The entry in row I and column J is Pij. There are two important conditions. First, every entry Pij must be non-negative because it is a probability. Second, the entries in each row must sum to 1 because from a current state I, the next state must be somewhere in the state space. A matrix with non-negative entries and rows that sum to 1 is called a stochastic matrix. In a Markov chain, each row represents a probability distribution over the next step. For example, consider the two-state matrix P equals row 1 0.8 and 0.2, row 2 0.4 and 0.6. If the current state is state 1, Then the chain stays in state 1 with probability 0.8 and moves to a state 2 with probability 0.2. If the current state is state 2, then it moves to state 1 with probability 0.4 and stays in state 2 with probability 0.6. The transition matrix is important because it lets us answer prediction questions using matrix multiplication. Okay, let us look at a simple weather example. Suppose the state space has two states, sunny and rainy. We use the transition matrix P with first row 0.8 and 0.2 and the second row 0.4 and 0.6. The first row corresponds to transitions from sunny. If today is sunny, then tomorrow is sunny with probability 0.8 and rainy with probability 0.2. The second row corresponds to transitions from rainy. If today is rainy, then tomorrow is sunny with probability 0.4 and rainy with probability 0.6. We can also draw this model as a directed graph. There is an arrow from sunny to sunny with probability 0.8 and an arrow from sunny to rainy with probability 0.2. This is the arrow. This should be erased. I'm going to remove the arrow in the center. Okay, I corrected it. So we have an arrow from sunny to rainy with probability 0.2. And an arrow from rainy to sunny with probability 0.2. Also an arrow from rainy to rainy with probability 0.6. This example shows how a Markov chain turns a qualitative process into a quantitative model. Once we have the transition probabilities, we can compute future probabilities, long-run behavior, and many other quantities. To predict the distribution of a Markov chain, we need two things, the initial distribution and the transition matrix. The initial distribution is usually written pi superscript 0. It gives the probabilities of the starting state. For a chain with m states, pi 0 is a row vector. P of x0 equals 1, P of x0 equals 2, up to P of x0 equals m. If we multiply this row vector by the transition matrix P, we get the distribution after one step. So pi 1 equals pi 0 times P. This one. After n steps, the distribution is pi n equals pi 0 times P to the power n. This is one of the most useful formulas in finite Markov chains. In the example on the slide, the initial distribution is 0.7 sunny and 0.3 rainy. The transition matrix is the same weather matrix. Multiplying gives pi 1 equals 0.68 and 0.32. This means that tomorrow the probability of sunny is 0.68 and the probability of rainy is 0.32. If we want the distribution after many days, we repeat the multiplication or compute P to the required power. This is how Markov chains perform short-run predictions. Okay, a one-step transition probability describes movement in one time step, but often we want to know the probability of moving from state I to state J after n steps. This is called an n-step transition probability. We write Pij superscript n equals P of xn equals j given x0 equals I. In a time homogeneous finite Markov chain, the matrix of all n-step transition probabilities is P to the power n. For the weather example, the transition matrix P is row 1 0.8, 0.2 and row 2 0.4, 0.6. If we compute P squared, we get row 1 0.72, 0.28 and row 2 0.56 and 0.44. This means, for example, that if today is sunny, the probability of rainy weather after 2 days is 0.28. This is the entry in the sunny row and rainy columns of P squared. The advantage of matrix powers is that we do not need to list all possible paths by hand. For 2 steps, the chain could go through several intermediate states. Matrix multiplication automatically sums over those possibilities. The Chapman-Kolmogorov equations explain why matrix powers work for Markov chains. They show how a long transition can be broken into shorter transitions. The formula is Pij superscript n plus m equals the sum over k of Pi k superscript n times P chi j superscript m. This means that to go from state I to state j in n plus m steps, we can first go from I to an intermediate state k in n steps and then go from k to j in m steps. We sum over all possible intermediate states k. In matrix form, the same formula becomes P to the power n plus m equals P to the power n times P to the power m. This is exactly the rule for multiplying transition matrices. The interpretation is very important. We split a path into 2 parts, the first n steps and the next m steps. The Markov property allows us to multiply the probabilities of these 2 parts conditional on the intermediate states. Then the law of total probability tells us to sum over all possible intermediate states. This equation is the foundation of both discrete time and continuous time Markov process theory. A Markov chain can be represented as a directed graph. In this graph, each state is a node. For example, this is a state 0, this is a state 1. We draw an arrow from state I to j if Pij is greater than 0. For example, the probability from state 1 to state 4 is 0.5 in this example. The arrow means that the chain can move from I to j in one step with positive probability. This graph representation is very useful for understanding the structure of the chain. Many important questions are really graph questions. For example, can a state I reach state j? Can a state j return to state I? Are there groups of states that communicate with each other? Are there states or classes that cannot be left once entered? The graph does not always show the exact probabilities unless we label the arrows, but it shows which transitions are possible. The possible paths determine concepts such as accessibility, communication, closed classes, recurrence, and transience. So when you receive a transition matrix, a good first step is to draw the directed graph. This makes the classification of states much easier and more visual. Okay, accessibility describes whether one state can be reached from another state. We say that state J is accessible from state I and right I arrow J if there exists some n greater than or equal to 0 such that Pij superscript n is greater than 0. In simple words, starting from I, it is possible to reach J in a finite number of steps. Communication is a two-way relationship. We say that I and J communicate and write it I double arrow J. In this way, if I can reach J and J can reach I, communication groups states into communicating classes. Okay, a communicating class is a set of states where every state can reach every other state in the set. Communication is an equivalence a relation, so it partitions the state space into disjoint classes. If the whole state space consists of only one communicating class, the chain is called irreducible. In an irreducible Markov chain, every state can eventually reach every other state. This idea is important because many long-run results become simpler for irreducible chains. For example, finite irreducible chains have unique stationary distributions. A closed class is a set of states that cannot be left once entered. Formally, a class C is closed if Pij equals 0 for every I in C and every j not in C. This means that from states inside C, there is no positive probability of moving outside C. An absorbing state is a special closed class containing only one state. State I is absorbing if Pii equals 1. If the chain enters an absorbing state, it stays there forever. Absorbing states are useful for modeling final outcomes. For example, in a reliability model, an absorbing state may represent system failure. In a game, it may represent winning or losing. In a project model, it may represent completion. In a medical model, it may represent recovery or death. The example matrix on the slide has three states. The third state has a P33 equal to 1, so state 3 is absorbing. Once the chain reaches state 3, it cannot move back to state 1 or 2. Closed classes and absorbing states help us understand where the process can end up in the long run. Recurrence and transience answer the question: if the chain starts in a state, will it return to that state or not? Let Ti be the first return time to state I. We define Ti as the minimum n greater than or equal to 1 such that xn equals I. A state I is recurrent if the probability of returning to I is 1 when starting from I. Mathematically, Pi of Ti less than infinity equals 1. A state is transient if the return probability is less than 1. This means that there is a positive probability that the chain leaves the state and never comes back. In a finite closed communicating class, all states are recurrent. Also, in a finite irreducible chain, all states are recurrent. This makes recurrence especially simple in many finite examples. It is important to understand that recurrence and transience are structural properties of the chain. They are not determined by one observed sample path. They depend on the transition probabilities and the possible path in the state graphs. In applications, recurrent states are states the process keeps revisiting, while transient states may disappear from the future behavior after some time. Periodicity describes whether returns to a state happen only at regular multiples of some number. The period of state I is defined as the greatest common divisor of all positive n, such that pii superscript n is greater than 0. If the period d of I equals 1, then state I is aperiodic. If the period is greater than 1, then the state is periodic. This simple example on the slide has two states and transition matrix row 1, 0, 1 and row 2, 1, 0. The chain always alternates between state 1 and state 2. If it starts in state 1, it returns to state 1 only at times 2, 4, 6, and so on. The greatest common divisor of these return times is 2, so state 1 has period 2. State 2 also has period 2. In an irreducible chain, all states have the same period. This means we can talk about the period of the whole irreducible chain. Periodicity is important for convergence. A finite irreducible chain may have a stationary distribution, but if it is periodic, the distribution from a fixed starting state may oscillate instead of converging. Okay, a stationary distribution is a probability distribution that does not change after one transition. We write it as pi equals pi p. It must also satisfy that the sum of pi I over all states equals 1 and each pi I is non-negative. The equation pi equals pi p means that if x0 has distribution pi, then x1 also has distribution pi. By repeating the same argument, xn has distribution pi for every n. So the distribution is stationary over time. Stationary distributions are important because they often describe long-run behavior. For example, pi I may represent the long-run fraction of time that the chain spends in state I. For finite irreducible Markov chains, a stationary distribution exists and is unique. However, we must be careful. Stationary does not always mean limiting from every starting state. A periodic chain can have a stationary distribution but still fail to converge from a fixed initial state. So a stationary distribution is an equilibrium distribution. It tells us what distribution remains unchanged by the transition dynamics. To find a stationary distribution, we solve a linear system. The equations are pi equals pi p together with the normalization equation that the components of pi sum to 1. Consider the two-state transition matrix with first row 0.8 and 0.2 and second row 0.3 and 0.7. Let pi equal pi 1 and pi 2. The stationary equation gives pi 1 equals 0.8, pi 1 plus 0.3, pi 2, and pi 2 equals 0.2 pi 1 plus 0.7 pi 2. These two equations. These two equations are dependent, so we also need the normalization equation pi 1 plus pi 2 equals 1. From the first equation, pi 1 minus 0.8 pi 1 equals 0.3 pi 2. So 0.2 pi 1 equals 0.3 pi 2. Therefore, pi 1 equals 1.5 pi 2. Now substitute into the normalization equation. We get 1.5 pi 2 plus pi 2 equals 1. So 2.5 pi 2 equals 1 and pi 2 equals 0.4. Then pi 1 equals 0.6. Therefore, the stationary distribution is pi equals 0.6 and 0.4. In the long run, if convergence holds, the chain spends about 60% of time in state 1 and 40% of time in state 2.